due to Grothendieck pitch, which gives a nuclearity criterion for a Kyoto sequence space. And as a corollary, we deduced that the space of smooth function or smooth functions on the torus, the space of holomorphic functions on the polydisk are nuclear. And also we proved that the class of nuclear spaces is stable under a number of natural operations. So let's recall this result. We proved that the class of nuclear spaces is stable under subspaces. That is, a subspace of a nuclear space is a nuclear space. Under quotients, that is the quotient of a nuclear space, modulo a vector subspace is also nuclear. It is stable under countable logically convex direct sums and under arbitrary products. It is also stable under completions. That is, the completion of a nuclear space is nuclear, and under the projective tensor products. They are uncompleted and they complete projective tensor products. By the way, the assumption that we consider only countable direct sums here is essential, and here is useful exercise. If you take an uncountable direct sum of many copies of the base field, where I is, the index set I is uncountable, then this space is not nuclear. It's not nuclear. In other words, the strongest locally convex space of an uncountable dimension is not nuclear. So the countability assumption here is essential. Now, by using this result, we can now essentially extend our class of examples of nuclear spaces. For examples of nuclear spaces. Example 1. Let's take the closed unit interval 0, 1, and let's embed it topologically to the circle by identifying the interval with the closed half circle. Clearly, this is a topological embedding. This embedding leads to the map, the restriction map from the space of smooth functions on the circle onto the space of smooth functions on the interval. And this map is easily seen to be surjective. This is a little exercise. So it is surjective. Now we apply the open mapping theorem. And we conclude that it is open. And so as a result, we may identify the space of smooth functions on the interval with a quotient of the space of smooth functions on the circle. But we already know that the space of smooth functions on the circle is nuclear. This was deduced from the Grothendieck criteria. As a result, we deduced that the space of smooth functions on the closed interval is also nuclear. And a similar argument shows that if we take the space of smooth functions on the closed cube, then it is also nuclear. I leave the details as an exercise for you, but this is more or less similar to the case of the closed interval. Example 2. Let's now take the space of smooth functions on Rn and observe that it is isomorphic to the projective limit of spaces of smooth functions on the closed cubes. The limit is taken over K. Now these spaces are nuclear, and it follows from our stability result. By the way, probably I should put it explicitly here, that the fact that this class of nuclear spaces is stable under subspaces and products really implies that it is stable under projective limits, because the projective limit of a system of locally convex spaces is isomorphic to a subspace of the product. So it is closed under arbitrary projective limits. And on the other hand, it is closed under countable inductive limits, because a countable inductive limit can be identified with a quotient of the direct sum. So if we now come back to this example, we see that C infinity of Rn is the projective limit of nuclear spaces, and so it is nuclear. Example 3. Example 3 generalizes example 2. Let's now take an arbitrary smooth real manifold, a smooth real manifold. And let's cover it by open sets, let's say UI, by countable many open sets, such that each of them is diffeomorphic to Rn. Then we can embed the space of smooth functions on M into the product of the spaces of smooth functions on the sets UI. So the embedding takes each function f to the family of its restrictions to the sets UI. And this map is already assumed to be topologically injective. So as a result, we see that C infinity of M is isomorphic to a subspace of the product of these spaces. But they are nuclear, by example 2. Their product is nuclear, because the product of nuclear spaces is nuclear, and the subspace of a nuclear space is again nuclear, so we can conclude that C infinity of M is nuclear. Another proof is as follows. Let's embed M into Rm for a suitable M by using the Whitney theorem, and deduce that C infinity of M is a quotient of C infinity of Rm. So it is nuclear. This is another proof of the same result. Example 4. Let's now consider the Schwarz space. So I claim that the Schwarz space on Rn is also nuclear. And to prove this, let's apply the following trick. Let's embed Rm into the n-dimensional sphere, where we identify the sphere with the one-point compactification of Rm. Then it's a simple but useful exercise to show that the Schwarz space over Rn is topologically isomorphic to the space of those smooth functions on the sphere, those functions f, such that f vanishes at infinity together with all partial derivatives. Together with all partial derivatives. This is a rather simple exercise which more or less readily follows from the definition of the Schwarz space. But we already know that the space of smooth functions on the sphere is nuclear, by the previous example. So the Schwarz space becomes a subspace of a nuclear space, and so it is also nuclear. Another proof uses, it is more analytic, and it uses the identification of the Schwarz space with a space of rapidly decreasing sequences. And to construct such an isomorphism, we can use the so-called Irving functions. We can find the details in the classic book by Reed and Simon, Methods of Mathematical Physics. Example 5. Let's now look at the space of smooth compactly supported functions. Again, we take a smooth real manifold. M. We take a compact, a countable compact exhaustion, Kn. The compact exhaustion of M. And we represent the space of smooth compactly supported functions on M as the locally convex inductive limit of the spaces of smooth functions supported at Kn. So the limit is taken over N. And each space here, C infinity Kn, let's say call that the space is equipped with the topology induced from C infinity of M. This is just the definition of the topology here. So we see that this space is nuclear. And we already know that a countable inductive limit of nuclear spaces is nuclear. So we conclude that the space of smooth compactly supported functions is nuclear. Example 6. We have a similar result about spaces of holomorphic functions on complex analytic manifolds. So if M is a complex manifold, then to prove the nuclearity of the space of holomorphic functions, we take an open cover of M by a family of open sets which are biolomorphically equivalent to open polydisks. Open n-dimensional polydisks. So now, just like in the case of the space of smooth functions, we can identify a space of holomorphic functions with a subspace of the product of the spaces of holomorphic functions on the open sets Ui. Again, every function f goes to the family of its restrictions to the sets Ui. And this map is easily seen to be topologically injective. But we already know that the space of holomorphic functions on the polydisk is nuclear. And again, the same argument as before shows that O of M is also nuclear. Example 7. Example 7. Let's take a compact subset K of Cn. Or more generally, we can take a compact subset of any complex manifold. And let's take a countable base of open neighborhoods of K. Base open neighborhoods of K. And let's look at the space of germs of holomorphic functions on K. The space of germs holomorphic functions at K. So the space is isomorphic to the locally convex inductive limit of the spaces O of Un. Well, that is already used. Let's let it be I instead of N. So this is the locally convex inductive limits of the spaces O of Ui. This is just the definition of the canonical topology of the space of germs. These spaces are nuclear, and the countable direct limit is also nuclear. So we conclude that O of K is nuclear. Okay, so these are the basic examples of nuclear spaces. So we now see that the class of nuclear spaces is indeed rather big. Our next goal is to discuss and to partially prove a very useful characterization of nuclearity in terms of tensor products. So tensor products and nuclear spaces. So we have the following theorem. Suppose that X and Y are locally convex spaces, such that one of them, for example, X, is nuclear. I claim that then the canonical maps from the projective tensor product of X and Y to the injective tensor product, as well as the respective map between the complete projective and injective tensor products. So these maps are topological isomorphisms. So we know that for Banach spaces this is not true, and we had discussed some concrete examples. For example, if you take little l1 here, the simplest example is if x is equal to little l1 and y is equal to little c0, then it's quite easy to show that these maps are not topological isomorphisms. And in fact, the second one is not surjective. Okay, so the proof of this result will be based on a couple of lemmas. Lemma 1. Suppose that X and Y are semi-normed spaces. Now let's consider the following map. This map takes the injective tensor product of X and Y, so let's note it by alpha, to the space of continuous operators, continuous linear operators from the dual of X to Y. So X prime, the dual of a semi-normed space, is a normed space, and we equip this space with the usual operator semi-norm, which is, by the way, a norm in the case where Y is a normed space. So alpha is given by the following formula. It is uniquely determined by the following rule. It takes every elementary tensor, or the following form, to the rank 1 operator, which takes every linear functional f on x to f of x, y. So clearly this map is well defined by the universal property of the algebraic tensor product. And what I claim that this map is an isometry. To prove this result, let's first observe that if we take any element in the tensor product then alpha of u is given by an explicit formula. Alpha of u takes every functional f to the following element. This is f tensor 1 applied to u. So u sits in x tensor y, f tensor 1 takes this space to y, and so alpha of u of f indeed sits in y. Well, is it true? This is true for the obvious reason that it is true on elementary tensors by construction, and every element in the tensor product is a finite sum of elementary tensors. So by linearity, this is true for every u. And now we calculate the injective tensor seminorm. So let's recall that by the definition, the injective tensor seminorm is the following supremum, where f and g run over the closed unit balls of the dual spaces, x prime and y prime, respectively. And let's write this in the following form: the supremum over f, the supremum over g. And now we write this element as the following composition. We apply g to f tensor 1. Now we look at this inner supremum over g. So this is a vector in y, and by the Helmholtz theorem, this inner supremum is nothing but the norm of this element. So the whole expression is equal to the supremum over f, of the norms of the following elements. But this is nothing but alpha of u applied to f. And so the whole expression is nothing but the operator seminorm of alpha of u. And this completes the proof. So we see that alpha is an S1. Number 2. Suppose we have 3 Banach spaces, x, y, and z. Banach spaces. And suppose that phi is a nuclear operator from x to y. And let's look at the following map. Phi tensor 1, which acts from x tensor z to y tensor z. And let's equip the space x tensor z with the injective tensor norm, and this one with the projective tensor norm. So I claim that in this case, this map will be continuous. This is not immediate because, well, of course, it is continuous if we put epsilon here and here, because epsilon is a functor, and it will be continuous if we put pi here and here. But the point is that if we put epsilon here and pi here, it is still continuous. Of course, this is not true for an arbitrary continuous linear map. But here we will use the assumption that phi is nuclear. To prove the result, we use our original definition of a nuclear operator between Banach spaces. So we have the canonical map from the completed projective tensor product of y and the dual of x to the space of operators from x to y, which takes, so let's note it by gamma. Gamma takes every elementary tensor of the form y tensor f to the following rank 1 operator. And since phi is nuclear, we see that phi is in the range of gamma. This is just our definition of a nuclear operator. So there exists an element u in the tensor product such that phi is gamma of u. And now we look at our map. So we want to prove that this map is continuous. And to prove the continuity of this map, we do the following trick. So first we replace here the projective tensor product by the completed projective tensor product. And we want to prove that this one is continuous. And we factorize this map, phi tensor 1, through the space of operators L of x prime z by means of lemma 1. So this is R alpha from lemma 1. Okay. And here we have another map beta given by the following formula. So what is beta of psi? Beta of psi is given by the following formula. So what does it mean? This is well defined because U sits in here, and one tensor psi. So psi takes x prime to z, and one tensor psi takes this space to y tensor z. So indeed, this element sits in this space. This is an element in here. Psi is an arbitrary operator from x prime to z. Now it's a simple exercise to show that beta is bounded or equivalently continuous, and the diagram commutes. And this completes the proof of our lemma. Because alpha and beta are continuous, so this one is also continuous. Well, this is not essential because this is just a dense subspace in here. So the norm is the same. The norm here is just a restriction of the norm here. Okay, now we are ready to prove our theorem. So let's recall that the theorem states that if we have a nuclear space X and an arbitrary locally convex space Y, then this canonical map is a topological isomorphism. Of course, it suffices to show that this one is a topological isomorphism because this one is obtained as the extension by continuity to the completions. Okay, so we take continuous seminorm P on X and a continuous seminorm R on Y. So to prove our result, it suffices to show that there exists another continuous seminorm Q on X such that the projective tensor seminorm P tensor Q, P tensor R is dominated by Q tensor, injective tensor, seminorm Q tensor R. Well, indeed, we know that every projective tensor seminorm is greater than or equal to the respective injective tensor seminorm. So if we prove this inequality, this will show that the injective tensor topology is stronger than the projective tensor topology, and as a result, they are the same. So we want to find Q, but we know that X is nuclear. So by nuclearity of X, there exists a continuous seminorm Q on X, such that the canonical map pi PQ, which acts between the associated bounded spaces XQ and XP, is nuclear. So let's show that this Q is exactly what we're looking for. So let's look at the following picture. This is the tensor product of X and Y. Here we take the tensor product of xp yes, xp and yr, so the associated Banach spaces, and we take their projective tensor product here. And here we take the tensor product of xq tilde and yr tilde. And here we take the injective tensor product. And we can consider the following commutative diagram. This is the tensor product of the canonical maps pi p and pi r. This is pi q tensor pi r, and this is pi p q tensor the identity map of yr. So obviously the diagram commutes. And now we calculate. So what we want to calculate? We calculate this seminorm p tensor r applied to u. So what is this? This is nothing but the norm of the image of u under this map. Pi p tensor pi q applied to u. I will take the projective tensor norm here. So why is it so? This is so because we have already observed in the previous lecture that there is an isometric isomorphism between the following Banach spaces. You take the projective tensor product of the associated Banach spaces. Then this is nothing but the Banach space associated to the projective tensor product. So as a result, this projective tensor seminorm comes from here, but these spaces are isomorphic, so we have this equality. So let's now continue this calculation. The diagram commutes, so this can be written as pi pq tensor 1 composed with pi q tensor pi r applied to u. And now let's look at the horizontal arrow. By number 2, this map is continuous if we put this with the projective tensor norm and this one with the ejective tensor norm. So this is continuous. So we can estimate this as a certain constant multiplied by the norm of this element. And here we take the injective tensor norm. Pi q tensor pi r. Applied to u, and we take the injective tensor norm here. And this is nothing but the injective tensor seminorm q tensor r applied to u. And that's it. So we see that this seminorm is dominated by this one. This completes the proof. Okay, so for nuclear spaces, if one of the spaces x and y is nuclear, then the projective and the injective tensor products are the same. In fact, this result can be generalized as follows. I have the following more general result. If X is a locally convex space, then the following conditions are equivalent. Condition 1, X is nuclear. Condition 2, for every locally convex space Z, for every locally convex space Y, the canonical map from the projective tensor product to the injective tensor product. For example, let's take the complete tensor products. is a topological isomorphism. And condition 3 is the same as condition 2, but for only one space little L1. The canonical map from the projective tensor product of X and little L1 to the injective tensor product of X and little L1 is a topological isomorphism. So we've just proved that 1 implies 2, and obviously 2 implies 3. But it turns out that 3 implies 1. The proof of this implication is essentially harder. It involves some auxiliary notions from the operator theory, such as absolutely summing operators. So this would require about 2 lectures. So we will not prove this result. But anyway, let me point out that this result really implies the Dvoretzky-Rogers theorem, which was mentioned some time ago at our lectures. If X is a Banach space, if X is an infinite dimensional Banach space, then we know that X is not nuclear. So by this result, this map is not a topological isomorphism. And this more or less easily implies by the open mapping theorem that it is not surjective. This map is not surjective. It turns out that if X is a Banach space, then this tensor product can be identified with the space of all absolutely convergent series in X. And this space can be identified with the space of all unconditionally convergent series. So this implies the Dvoretzky-Rogers theorem, which states that in any infinite dimensional Banach space, there exists an unconditionally convergent series, which is not absolutely convergent. Now, this theorem, as well as most results about nuclear spaces, is due to Grothendieck, with some extra remarks due to Peach. So, strictly speaking, this is the theorem is due to Grothendieck and Peach. As far as I remember, Grothendieck proved this for Fouché spaces, and Peach observed that the same argument can be modified to show that it works for an arbitrary local conic space. Okay. In fact, Grothendieck in 1952, Grothendieck made the following conjecture. Which is quite natural by looking at the theorem, that if X is a locally conic space, and if there exists at least one non-nuclear locally convex space Y, such that this canonical map is an isomorphism, is a topological isomorphism, then X is nuclear. In other words, he conjectured that maybe we can replace here L1 by an arbitrary non-nuclear locally convex space. And this was an open problem for more than 30 years. A counterexample was found by Pizier in 1983. He proved that there exists constructed a Banach space, an infinite dimensional Banach space, an infinite dimensional Banach space P is for Pizier, such that the canonical map from the projective tensor product of P by itself to the injective tensor product of P by itself is a topological isomorphism. This is quite trivial because if you take any classical Banach space, like say little L1, little L2, big OP spaces, spaces of continuous functions, and so on, for all of them, this space is not, this map is not a topological isomorphism. So Pizier's construction was quite involved. And what is also quite remarkable is that if we replace here double tensor products by triple tensor products, then we actually get a characterization of nuclearity. The following theorem was proved by, let me write it down, that's the next, let me put it here. So the following result was proved by Camille Young in 1982, if I'm not mistaken. So his second name is often mispronounced as John by many people, but in fact the correct pronunciation is Young, this Czech mathematician. And he proved that if X is a locally convex space, such that the canonical map from the triple projective tensor product, X tensor X tensor X, to the triple injective tensor product. If this map is a topological isomorphism, then X has to be nuclear. Very nice result. Okay, so now to continue our study of nuclear spaces, we have to make a short digression into the theory of topological tensor products, and to prove a remarkable property of tensor products, which states that the projective and injective tensor products often commute with projective limits. Tensor products and projective limits. So let's start with some definitions. Suppose that we have a projective system of locally convex spaces. Projective system of locally convex spaces, and let phi I be the canonical map so let X denote the projective limit. X is the projective limit of this system. And let phi I denote the canonical map from X to Xi. We say that this system is reduced. The projective system is reduced if all these maps phi I have dense ranges. Every I. And in this case, we say that X is a reduced projective limit. A reduced projective limit. So a reduced projective limit is just the projective limit of a reduced projective system. In fact, almost all concrete examples of projective limits, which we discussed before, are in fact reduced. And this is due to the following very general example. If X is a complete locally convex space, and P is a directed defining family of semi-norms, X. So we know that in this case, X is topologically isomorphic to the projective limit of the associated bound spaces, X P tilde. And just by the construction of these spaces, X P tilde, this is a reduced projective limit. So let's recall that to construct X P tilde, X P tilde is the completion of the quotient of X modulo the subspace where P vanishes equipped with the quotient word. So just by construction, the canonical map from X to X P tilde has dense range. And all concrete examples of projective limits that we discussed before are actually special cases of this construction. So they are reduced. So as a result, we see that this property is very natural because it often appears in concrete situations. So I claim that we have the following result. Suppose we have two reduced projective systems of locally convex spaces, xi, phi ij, and say yk, psi kl. Reduced projective systems of locally convex spaces. So let phi I denote the canonical map of x to xi, and psi k the canonical map of y onto yk, where x and y are just the projective limits. X is the projective limit of xi, and y is the projective limit of yk. I claim that there exists a unique topological isomorphism between the complete projective or injective tensor product of x and y and the projective limit of the tensor product system xi tensor yk, which is defined in the obvious way, such that the following diagram commutes. So if we put here xi tensor yk, this is the canonical, the product, the tensor product of phi I and psi k, and here we have the canonical map of the projective system tau ik. Let's denote this isomorphism by chi. There exists a unique topological isomorphism such that this diagram commutes for every I and every k. So you should ask me which kind of tensor product do we consider here? And the answer is A of the projective and the injective tensor products works. So here the complete tensor product is either the projective tensor product or the injective tensor product. In both cases, the result is true. So the complete projective tensor product and the complete injective tensor product commutes. Each of them commutes with reduced projective limits. But this is quite an unexpected result because it doesn't follow from the category theoretic properties of limits and tensor products. And in the pure algebraic setting, there is no such result. The algebraic tensor product usually doesn't commute with the projective limits. To prove this result, we need the following simple lemma. Suppose that we have semi-normed spaces x1, y1, x2, and y2, semi-normed spaces, and two continuous linear maps phi k from xk to yk, which are isometries with dense ranges. Isometries with dense ranges. I claim that the projective tensor product is also an isometry. And the same is true for the injective tensor product. Well, for the injective tensor product, this is trivial, because we have already proved that the injective tensor product always preserves isometries. The projective tensor product doesn't preserve isometries in the general case, but here we have isometries with dense ranges. So it's an exercise for you to prove this for the projective tensor product. A hint is that each phi chi extends to an isometric isomorphism between the completions. Isometric isomorphism between the completions. This is more or less clear. And then use the fact that the projective tensor product of two isometric isomorphism is an isometric isomorphism. Okay, now we are ready to prove our theorem. Proof of theorem. The existence of chi is immediate from the universal property of tensor products and projective limits. The existence, the uniqueness, and the continuity. And also, since each map to I chi has dense range, this is more or less clear from the construction, that it follows that chi also has dense range. So there exists a unique continuous linear map chi between the respective spaces. Such that the diagram commutes. This follows from the universal property, and I also claim that chi has dense range. Well, this is an exercise for you, but actually it is immediate from the commutativity of the diagram. And another old exercise, which was discussed some time ago, that if you have a vector subspace in the projective limit, it will be dense provided that its images in the respective spaces here will be dense. This exercise was already used 2 or 3 times in our course, and now so we use it again. So since the range of this arrow is dense, it follows that if we take the range of chi, it will be dense in here. So the only point is to show that chi the only point is to show that chi is topologically injective. This will complete the proof. So let's prove the topological injectivity. So let's look at our diagram once again. Basically, what I want to do is to show that we can find compatible defining families of seminorms here and here, such that chi will be isometric with respect to each of them. So let's draw this picture once again by specifying the seminorms on our spaces. So we take a seminorm, a continuous seminorm P on xi and P on xi. And Q on yk. And let's consider the tensor product of xi and yk equipped with P tensor Q. So again, we can take either the projective tensor seminorm or the injective tensor seminorm. This doesn't matter. So here we have x tensor y. This is the canonical map phi I tensor psi k. And we equip this space with the following seminorm P phi I tensor Q psi k. So what can now we say about this map? I claim that this is an isometry by lemma. Phi I has dense range, psi I has dense range, and each of them is an isometry with respect to these seminorms, just by construction. Okay, this is an isometry. Now we take here the projective limit of, for convenience, we take the uncompleted tensor products, xi tensor yk, and we equip this space with the seminorm p tensor q composed with tau ik. In other words, we choose the seminorm here in such a way that this canonical map tau ik is also in isometry, just by construction. We define seminorms here and here in such a way that it is in isometry. But now the diagram commutes. And so we see that chi is an isometry with respect to this seminorm here and this seminorm here. Chi is an isometry with respect to p phi I tensor q psi k and p tensor q composed with tau ik. And to complete the proof, it suffices to observe that if P runs over the family of all continuous seminorms on Xi, Q runs over the family of all continuous seminorm on over Yk, and the indices I and K run over the respective index sets. So as a result, we get a defining family of seminorms here, and we get a defining family of seminorms here, just by definition of the projective locally convex topology. So this implies that this is true. This is true for every P, every Q, every I, and every K. And this implies that kappa is, sorry, not kappa, but chi is topologically injective. And this completes the proof. So it is continuous, topologically injective, as it has dense range, and acts between complete spaces. So it is a topological isomorphism. That's it. As a corollary, we see that the complete projective tensor product and the complete injective tensor product commute with products. If you have a product, of a family of locally convex spaces Xi, and the product of a family of locally convex spaces Yk, then their projective tensor product or the injective tensor product are isomorphic to the product of their tensor products. Again, this is true for the projective tensor product and for the injective tensor product as well. Well, indeed, to prove this result, let's just recall that the product, the locally convex product, is, so let me write it down explicitly. The product of Xi is isomorphic to the projective limit of products taken over finite sets. So here, fragment of I denotes the collection of all finite subsets of I. And this is obviously reduced projective limit, because the canonical map from here to the finite product is surjective. So we see that this corollary follows from the previous theorem. And again, I'd like to stress once again that this is false for the algebraic tensor product. So in some sense, the projective and the complete projective and injective tensor products are, in some situations, they behave better than the algebraic tensor product. As a corollary of this result, let's show a rather unexpected property of the complete injective tensor product. So I claim that the complete injective tensor product commutes, the complete injective tensor product preserves the injectivity of linear maps. Theorem. if we have complete locally convex spaces xk and yk, x1, y1, x2, and y2, complete locally convex spaces, and two injective linear maps phi k from xk to yk. I claim that their completed injective tensor product is also injective. This is quite unexpected because, well, in general, the injectivity in functional analysis is an unstable property. In the sense that it is not stable under anything reasonable. For example, if you have an injective map between normal spaces and we extend it by continuity to the completions, then in general it is no longer injective. And if we take again an injective map between balanced spaces and take a small perturbation by norm, then the result is not necessarily injective. But in this case, in this sense, the injectivity is stable. This is just a kind of exception of the general rule. The proof is based again on a couple of lemmas. So let's recall that if X is a normed space and Y is a locally convex space, then we denote by LB of XY the space of continuous linear operators from X to Y equipped with the topology of uniform convergence. The topology of uniform convergence on the closed unit ball. Of the closed unit ball of X. Number one, if X is a normed space, and if we have a projective system of locally convex spaces yi, projective system of locally convex spaces, then we have the following topological isomorphism. There exists a topological isomorphism between the space LB from X to the projective limit of the spaces II and the projective limit of the spaces of linear operators from X to YI. Well, the proof is actually a simple exercise. Let's observe that these vector spaces are isomorphic canonically just by the very definition of the projective limit. If we recall now the definition of the projective limit, this is just the existence of a vector space isomorphism between these two spaces. So the only thing to show is that this isomorphism is a topological isomorphism. But this readily follows from the explicit defining families of seminorms on the respective spaces. As a corollary, we see that if X is a normed space and Y is a complete locally convex space, then LB of XY is complete. Well, indeed, we can represent Y as the projective limit of one spaces because it is complete. So LB of XY will be isomorphic to the projective limit of the spaces LB of XYI. And this is the space of all bounded linear operators from X to YI. X is a normed space, YI is a bound space, and it's a standard result of functional analysis that this is also a bound space. This is a bound space, so as a result we get a complete locally convex space. Number two extends our earlier result about seminormed spaces. If X is normed space and Y is Hausdorff locally convex space, then the following map. This is our map alpha, which was discussed before in the case of semi-Nernst spaces. It acts from the injective tensor product of x and y to LB of x prime y by the following rule. So this map is topologically injective. And part 2, if y is complete, then alpha extends to a topologically injective map from the complete injective tensor product of x and y to LB of x prime y. The proof of part 1 is an exercise, so everything is reduced to the case of semi-Nernst spaces. We already know that in the case of semi-Nernst spaces, this is an isometry, and the general case is reduced to semi-Nernst spaces. And part 2 follows from part 1, modulo the fact that modulo the previous corollary. So we know that this space is complete, and we have a topologically injective map from here to this space, but this space is complete, so this topological embedding extends to a topological embedding of the completion to the same space. Okay, we can now prove our theorem. So let's recall that we want to show that the injective tensor product, the complete injective tensor product of two injective maps is injective. Well, first of all, let's simplify our task by observing that we have the following decomposition. So this is the identity map of x1, and this is the identity map of y2. So this is obviously true. So everything is reduced to one of these two maps. So it now suffices to show that if x, y, and z are complete locally convex spaces, and phi is an injective continuous linear map from x to y, then the injective tensor product of the identity map of z and phi is also injective. Okay, to prove this result, let's first assume that z is a Banach space. Case 1, z is a Banach space. In this case, we have the following picture. So z tensor x, z tensor y. This is our map 1 tensor phi. Here we have the embedding of the space into L of z prime x, and into LB of z prime x, and this embeds into LB from z prime to y. And here we have a map from here to here, which is also induced by phi. It takes every psi, so psi sits in here, to psi composed with phi. And it's immediate to show that the diagonal commutes, just by construction. But the bottom arrow is obviously injective. If phi, if psi is, if this composition is 0, then psi is necessarily 0 because phi is injective. So the top horizontal arrow is also injective. And this completes the proof. Okay. Okay, so that's all for today. At the next lecture, this will be the last lecture. At the next lecture, we deduce from today's results a nice exactness property of the complete projective and injective of a complete projective tensor product for nuclear spaces, for nuclear Fisher spaces, and deduce an important theorem about projective tensor products of spaces of smooth and homomorphic functions on real respectively complex manifolds. And we also discuss, briefly discuss some applications of nuclear spaces to complex analytic geometry.
Я совсем забыл, что такое ЛБ. Что-то я...
ЛБ это... So we take a norm space X and a locally convex space Y. We consider the space of all continuous linear maps from X to Y. And we equip it with the topology of uniform convergence on the closed unit ball. So explicitly, we can write a defining family of semi-norms. If say, Q is a defining family of semi-norms on Y, each such semi-norm defines a semi-norm on this space, Q tilde. This is a semi-norm on L of xy, given by the following formula. Q tilde of T is the supremum of Q of T of X, where X runs over the closed unit ball. And the family of all such semi-norms Q tilde, where Q runs over Q, generates this topology, generates the topology on LB. And this is the topology of uniform convergence on the closed unit ball, just by definition. This is a special case on what we discussed before. If X is an arbitrary locally convex space, not necessarily normed, we can equip L of xy with the topology of uniform convergence on bounded subsets of X. So we replace here the unit ball by an arbitrary bounded subset of X, and we consider all Q and all bounded sets. So in this case, the defining family of semi-norms on L of xy will be indexed by Q and by the family of all bounded subsets of X. But this is a special case. X is a norm space, and we don't have to consider all bounded sets. It suffices to take the closed unit ball, and the topology will be the same. So this is just a natural generalization of the norm space L of xy, where X and Y are both norm spaces.
Mm-hmm.